Wow, and then just say after that. And then I started doing some work. Not bad. That's like a 5 to 10. Like, I shouldn't agree to it. I knew even when I agreed to it, I wasn't going to have time. But now I have to just do it for once before I can do it.
Yeah, I checked it yesterday. Hey, good morning. Happy Valentine's Day. I'll skip any jokes about may you fit the parameters of your loved one's heart and so on. All right, so today we're going to talk about fitting and alignment. Mainly today we're going to talk about fitting, and then we're going to talk about alignment and recognition in the next class. And fitting is, they're both basically the same problem. The only difference is that fitting is finding the parameters of a model that best fits the data. For example, you fit a line to a set of points or a circle to a set of points. Alignment is finding the parameters that best matches two sets of points. So you have a set of corresponding points, and you want to find the parameters of a transformation such that one set of points is projected near the other set of corresponding points. They end up being solved by the same kinds of tools. So let's get into it. So one thing to note, actually, for people watching the video, now there's some empty seats, so probably some people that are watching from the comfort of their homes can enjoy the discomfort of the classroom if that's your preference. So the main challenges of designing a fitting and alignment algorithm are to basically create, one of the main ones is to create a suitable goodness of fit measure. So that should be really basic. You need to know, does my proposed model fit the data? How do I measure whether my proposed model fits the data? So generically, the similarity should reflect the application goals. So if you're trying to, for example, predict some variable given some other variable, then you care how good the prediction is. If you're trying to geometrically fit a line to a set of points, then you might have a different criteria, as I'll show in a bit. The other thing is that your goodness of fit measure can differ quite a lot depending on whether you expect there to be a lot of noise and outliers. So it might be that you want all the points to fit the data, or that you only want a large subset of the points to fit the data. Another key design challenge is designing the optimization method. So once you know what your model is and you know how to say whether your model is good, then you need to try to solve for the parameters of the model that maximize your goodness of fit. And sometimes it's pretty simple, like in least squares methods, and other times it requires some kind of more complex strategy, doing a grid search, doing beam search, doing some nonlinear optimization, and so on. So here you want to try to, often the challenge is trying to avoid local optima. So that means that you want to find the best solution, not just a solution such that if you slightly change the parameters, it gets worse. And you want to try to find the best parameters quickly. So I'm going to talk about several different methods. So it's kind of a survey of your tool set for fitting and alignment. And these methods, I'm going to use line fitting as an example, but these methods will also pop up throughout the semester because they're used for photo stitching to create panoramas. They're used for structure from motion. They're used for object instance recognition. They're used for basically any time that you're trying to align images to each other or trying to align an object of a model of an object to a region. You're using some kind of fitting or alignment method, as well as a lot of medical image analysis. Basically, fitting and alignment is one of the fundamental problems of computer vision. So we're going to talk about some global optimization methods, like least squares fit, robust least squares, and most likely next class we'll get to iterative closest point. So these are just trying to directly solve for the parameters that best fit the data. And then we'll also talk about some hypothesize and test methods, where these methods, you propose some set of parameters, and there's a variety of ways that you can propose those parameters, and then you test to see how good those parameters are. And so generally, the global optimization or search for parameters tends to work well when you expect that your data is just noisy, but there's not a lot of outliers. And hypothesize and test tend to be more robust to outliers. An outlier just means that it's a point that doesn't fit your data at all. So it's not just perturbed by noise, but it's like a complete mismatch to your model. So one example would be if you're trying to match points between two images, if some of your matches are wrong, then that's an outlier, because the transformation that you're trying to find won't explain that relationship at all. On the other hand, if your points were just detected a pixel off from where they truly were, that would be noise, because the points still fit the model, but it's just that the transformation won't be able to exactly map one onto the other because the detection was off by a pixel. Right. So I'm going to do, as an example for all these methods, I'm going to do line fitting, because it's a simple example, but there's actually a lot of variations to how we can solve this problem. So just to note down some notation. So the problem is that we've got some set of points. Do these show up? Yeah, they show up. All right, I'll do x's. So I've got some set of points here. And these points are at some position, which I'll call xi, yi. And I'm trying to fit some line to them, right? And so these points have some noise. If I say that these points came from a line model, then there's a little bit of noise because they won't all fall exactly on some line. If I had an outlier, though, it might appear way over here. And depending on my goodness of fit measure, might completely warp the direction of my line or might shift it over. All right, so let's go with the simplest method first, or one of the most common fitting methods, which is just least squares. So here I would formulate this by first saying, what is my objective function? So let's first just say that we're going to denote a line by y equals mx, plus b, or I'll say for any ith point, y equals mx, yi equals mxi plus b. And now if I've got a set of points, then my error is the sum over all the points. So I could say I equals 1 to n of mxi plus b minus yi. So this least squares example might be familiar or even boring to many of you. But I think it's worth going through in detail for some of you that aren't as don't solve systems of linear equations as often. It gives you a little bit of background, and for the rest of you, it will sort of get you into the mode of solving these kinds of problems. So, all right, so now the first thing I usually want to do is just write this in matrix form. So I can write this as my error is first, I want to separate out the variables that I'm solving for, which in this case is m and b. And so m and b, the slope and y-intercept, are my unknowns, and xi and yi are my knowns. They're the points. So I'm given a set of points, and I want to try to solve for the line parameters. So I can just write this as xi1 times mb minus yi squared. Or I can write it in, I can also write this, this entire expression can be written out as, let's see, xi1, or x11, x21, dot, 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 xn1, times mb minus y1, y2, dot, 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 yn. Okay, so I'm saying, so I've just written the same thing as I want to minimize the L2 norm of this vector, which will be the difference between my prediction, which is xi m times b, plus b, so I want to minimize that prediction with y, which is the thing that I'm trying to predict, if you think of it that way. All right, and so I can just rewrite this as my error is some minimizing some A transpose, or just AP, minus Y, where A is now this vector of knowns. It's my coefficient matrix, and often you'll find that things get into this form. Y is a vector of knowns. It's the thing that I'm trying to predict, and P are my variables. So this is equal to Y transpose Y minus 2 times A P transpose Y plus A transpose A, or P transpose A transpose AP. So now if I want to solve this, I can take their derivative with respect to, let me just check in my notes to make sure I didn't make any mistakes, which is easy when you try to talk and write at the same time. P transpose blah, blah, blah. Okay. All right, so now I can solve this by taking the typical way that you solve some, I want to try to find the minimum of this. So E is my error. I want to minimize this. So I take the derivative with respect to my variables P. So I want to take the derivative with respect to this vector. Whenever I take derivatives with respect to vectors or matrices, I often have to look up stuff about like how do you deal with the transposes. But it's basically pretty similar to scalars. You just need to be careful about, like, when you do the derivative of P transpose AP, do you keep the P transpose or do you keep the P? So if I take the derivative of E with respect to my vector P, then that's equal to, so the derivative of Y transpose Y is, of course, 0. Then the derivative of this term here is minus 2, should be minus 2ay, a transpose y. And then the derivative of this term here, it's kind of like if I have ax squared, the derivative is 2ax. So here I've kind of got like a squared because I've got a p transpose p with some matrix in the middle of it. So the derivative is 2 times sorry, I need to remember which one, if I get the transpose or transpose, a transpose, wait, let me look at my notes, sorry about this. 2, oh, wait, okay. So plus 2 times a transpose AP. And so then I set this equal to 0 because I'll reach the minimum when my derivative with respect to p is equal to 0. So if I move this over to the right-hand side, then I have a transpose AP equals a transpose y. And so I get p equals a transpose a inverse a transpose y. Right. And then this is just the pseudo-inverse of a. So it's basically of the form, I've got my error function here tells me that I've got something of the form a times my variables p equals some set of constants y, or I want it to be as close as possible to equals. And so the solution is just the pseudo-inverse of a, which is a transpose a inverse a transpose, times y. Right, that's all written down there. And so in MATLAB, this becomes a lot shorter. It's just p equals a backslash y. So the reason why this is better to do than doing a transpose a inverse a transpose, because one, it's faster, and it's also more numerically stable. So you don't have to, taking inverses can, since you're taking an inverse but then multiplying it by a component of the inverse, if the inverse is not, if you've got like some kinds of numerical rounding or whatever in the inverse, then this reduces the instability due to that. Okay, so I want to just work out that example because this kinds of least squares fitting is something that you might do to solve affine projections or many other kinds of linear projections. So you might go through that exercise yourself sometime. So what is the problem with this? So I've done a least squares where I say that I'm trying to minimize the prediction of the y value of my point to the line, right? I'm trying to minimize mx plus b minus y. So what's the problem with this? Yes? The comment was it lacks robustness to noise. Sort of. So if your noise is, say, a Gaussian noise or some kind of noise about the prediction, it's actually about as good as you can do. So it does depend. It depends on your noise model, but generically, that's going to be. It does lack robustness to outliers. That's true. Yeah. Question? Statement. Yeah, so if what I'm trying to predict is how much money somebody makes as they get older, then this measure might make sense. But if what I'm trying to do is fit a point geometrically to the line, then it's not a good measure, right? Because these points are actually closer to the lines than that error measure indicates. And Another way to say it is that another issue with that that's related is that it's not rotationally invariant. So as the line rotates, and if you move the points with the line, then their error measure will change if you move them according to the same rotation. And if you imagine that you had a vertical line, so you're trying to fit points to a vertical line, then the error goes to infinity if they're like moving around randomly in the xy coordinates. Question?
In the previous slide, you mentioned that outliers can completely skew the line fitting that you're doing.
Yes.
So do you remove the outliers from the data set, or no?
I will show you methods to deal with outliers. So this method so far, and I've got a demo too. So I'll show you that this method so far does not deal with outliers. You need some way to deal with it. So it's sort of like an inner algorithm in an outlier removing algorithm. So like, for example, ransack, which we'll get to, uses, you may use a least squares fit on a subset of points and then test to see how many points agree with the fit to that subset. And that way, you're checking to see what % of all your points agree instead of fitting something to all the points. But, well, you don't know. I mean, that would be the ideal thing to do, but you didn't introduce them on purpose, so you don't know which points are outliers. So, for example, if you're doing, the question was why not just remove the outliers? So, if you're doing a homography, so you're matching 2 images taken from the same position at different angles, and you find correspondences between the points, you don't know which of those correspondences are correct a priori, and you also don't have a model for the transformation, so you've got a chicken and egg problem where if you knew the transformation, then you would know where the outliers are, and if you knew where the outliers were, then you could solve for the transformation just using least squares. But since you don't know either, you have to kind of make some guesses and then check to see how many points agree with those guesses. Okay, so to deal with the aforementioned problems, well, actually only to deal with the ones I had on the slide. This doesn't deal with outliers yet. We can use total least squares. So I don't know, total, I guess, is because it's totally awesome compared to regular least squares. So this is using the homogeneous line equation. So we've got, instead of modeling a line as mx plus b equals y, we're going to model a line as ax plus by plus c equals 0. So this is actually a convenient form of a line. This is a convenient way to model lines for a lot of kinds of operations. So if, one thing that's nice about it is that if a squared plus b squared is equal to 1. And note that you can scale a, b, and c freely, because if you multiply them all by any scalar, then you've still got 0 on the right-hand side. So if a squared plus b squared equals 1, then the distance between some point and the line is just the absolute value of axi plus byi plus c. So it's nice that we've got such a simple line to distance, point to line distance function. Also, what's nice is that the normal is just a and b. So there's a variety of other things that are nice about this form that we'll get to once it's more relevant. So all right, so now we want to find ABC to minimize the sum of squared perpendicular distances. Right, this is probably a better measure if what we're trying to do is have a geometric fit of the point to the line. And so again, I can write this as, since this equation will be equal, since ax plus by plus c will be equal to 0, if I've got a perfect fit, then it makes sense that I want to minimize the squared value of ax plus by plus c. So again, I've got to sum over all my points. I can take the derivative with respect to c, and now because I had the outside squared, then the derivative is just 2 times the inner part of that parentheses. Solve with respect to c, and then I get c is just negative a times the mean of x minus b times the mean of y. So all I did here, took the derivative with respect to c to get here. Then I do then I've got the sum over 2c, which is just going to be 2n times c. So I brought c over to this side. So then I divide by negative 2 over n. And that gives me my negative a, pulling that out of the summation of xi minus b over n, summation of yi. This bar is often used to denote a mean, if you see like a variable with a bar over it. But I'll usually point that out if I use that. OK, so then again, I can write this in matrix form. And so now I get my, I can plug in negative a mean of x minus b mean of y for c. And now I only need to solve for a and b. So now when I write this into matrix form, my coefficients for every row are the x of that row minus the mean of x, and the y of that row minus the mean of y. And then, so I've got this, my A matrix, my matrix of coefficients. And I'm just trying to minimize this whole thing. So here I'm writing it in vector matrix form. All right. So so now I could try to do like my least squares pseudo-inverse solver or whatever. There's a problem, though, which is that I've got a trivial solution here, right? If I just set p equals 0, then I've minimized it. And so I don't want to let p equal 0. Also, remember that setting p equals 0 would violate the assumption under which this is actually a distance. Remember that this is the distance, going back to this slide, if a squared plus b squared equals 1. So I need to fix a squared plus b squared equals 1. And so really I want to minimize p transpose AP such that p transpose p equals 1. So there's actually a nice, a very easy way to show the solution of this is using Lagrange multipliers. Let me just switch over to do that. So I'm trying to minimize p transpose AP such that p transpose p equals 1. All right, it'll take it a while to settle down. So I can just do this as, so I can write that as minimize, I'm just going to do a dot for the rest of the mi's, and p transpose AP plus lambda times 1 minus p transpose p. Now I can do that because I've said that p transpose p equals 1, so this is just 0 for any lambda. Now I take the derivative with respect to p, and I get, so derivative of that thing with respect to p gives me a transpose AP minus lambda p is equal to, setting that equal to 0 will give me my minimum or maximum. Then a transpose AP is equal to lambda p. And this is basically the definition of an eigenvector. So an eigenvector, if you have ax equals lambda x, and the eigenvectors of A will satisfy that equation, right? So the eigenvectors of A transpose A will satisfy this equation, and the solution and then the value of P transpose AP will be equal to lambda. So I want the eigenvector that corresponds to the smallest eigenvalue. So if I then just plug in that, so if I plug in, if I write this as minimizing, uh-oh, is my pen dying? Okay, good. P transpose P So I can also write that I want to minimize P transpose A transpose P over P actually, let me just do that a little bit more easily. So I'm going to say P transpose AP. Okay, so I can just simply write, since the value that I'm trying to minimize is P transpose A transpose AP, then I can substitute lambda P for A transpose AP. And so then I've got lambda P transpose P is the value after I've found one of these critical points through the eigenvectors. And since P transpose P is equal to 1, eigenvectors have a length of 1, then this gives me that the value of the function that I'm trying to minimize is lambda. So in summary, the solution to this system of homogeneous equations is the eigenvector of A transpose A that corresponds to the smallest eigenvalue. Let me switch over. So there's actually a couple of ways to derive this that you can find if you want to go through the derivation more slowly on the Wikipedia page. Often, if you've got something if you're trying to minimize something subject to a constraint, I find that often using the Lagrange multiplier is the easiest way to solve it. But you can also just try to directly minimize this expression as well. Okay, so to recap, we've addressed two common optimization problems. And even though I've only addressed them in the context of line fitting, you'll see these same kinds of problems show up all over the place. So one of the problems is that you're trying to minimize ax minus b squared, or the norm of ax minus b. And the solution is which is a least squares solution to ax equals b, where b is non-zero. Then the solution is just a pseudo-inverse of a times b. So this problem shows up, for example, when you're trying to solve for homography, which is a plane-to-plane mapping, or a mapping from points on one image to another image where the only difference between the images is a rotation. The other kind of problem that's really common to see, actually, the second one is for the homography. The first one would be, for example, if you're trying to solve for a affine transformation between two sets of points. The second kind of problem that you run into is where you've got a homogeneous system of linear equations. A homogeneous system is just one where you've got ax equals 0. So you've got a 0 on the right-hand side, so there's a trivial solution. You need to avoid the trivial solution typically by saying that your solution must have a norm of 1. So then you've got your problem statement is that you've got x transpose ax such that x transpose x equals 0. So I want to minimize this quadratic expression, but I want my solution to have a length of 1. Or equivalently, you can say I want to minimize A transpose AX over X transpose X. That's equivalent because if this is equal to 1, then this is just dividing by 1. But it leads to a different way of deriving the solution. So the solution to this is just that you find the eigenvectors of A transpose A and their corresponding eigenvalues. You would want to use a math package for this, like Eig in MATLAB. And then you want to choose the eigenvector that corresponds to the smallest eigenvalue. One thing to note is that in MATLAB, there's two functions for computing eigenvectors. There's Eig and Eigs. And they have a different ordering on whether the first eigenvector is the largest or the smallest. So make sure that if you're solving this way that you check to see that you're taking the eigenvector that corresponds to the smallest eigenvalue and not the one that corresponds to the largest eigenvalue. Eigs is for doing eigenvectors as sparse matrices, but you can, I think, use it on either. So far we've talked about a couple methods for least squares, global optimization, where you're trying to fit all the points. So what I mean by global is you're fitting all the points that are given to you. On the plus side, we've got a clearly specified objective. The goodness of fit measure is really easy to write down. The optimization is also really easy. It's just solving a system of linear equations. You really can't get easier than that for optimization. The downside is that it might not be what you want to optimize. So in particular, you might have outliers that don't fit your model, and this will be give you a bad result. And it also only lets you get one fit to the data. So you might, for example, have a set of points that you think might fit several lines. You want to do like a piecewise linear fit, or you just want to fit a set of lines or a set of circles to the data. And so this only lets you fit one model to all the data. So we'll introduce in a bit some methods that can deal with this. So first is a simple method to deal with the outliers. The idea is that we're going to change our objective function. So instead of saying that we have a squared error or a squared loss for the distance of the points to the lines, we're going to let the loss kind of reach some maximum. So the problem with the squared loss is that as you get further away from the true value, your error increases quadratically. Right? So if you've got some point that's an outlier that's really far from your model, its error term is going to dominate your whole solution. So we want some robust loss. So these losses basically say that the most you'll ever pay for an error is 1. So if your point is like 4 off from the model, then your error is approximately 1. And if it's 500 off from the model, then your error is still approximately 1. So this will mean that you pay a price for not fitting a point, but that price doesn't go to infinity as the error increases. So the loss function that's used here is that so u is like your error of a point fitting your model. And so it's the error squared over some sigma squared plus the error squared. And since depending on your sigma, these are different values of sigma, you have different sensitivity to the distance of points to your model. So this is how we can estimate this. So the solution is an iterative solution where you try to estimate your sigma, which is your error tolerance. That kind of models how much noise is in the system. And so you choose a sigma, and then you minimize your error according to that robust error function. And then you choose a new sigma, and then you keep on repeating until you converge. So the algorithm is that you choose some theta by least squares fit. So you just do a least squares fit to all your data. And then you say that sigma is 1.5 times the median error. There's actually a reason for that 1.5, and I think it's actually 1.49 and then a whole bunch of like decimals. But unless you're like super interested specifically in this function, it's not worth spending a long time in explaining, and I don't even remember anyway, why it's 1.5. So so you choose 1.5, sigma is 1.5 times the median error. Then you choose the parameters to minimize this error function, which is the error. So the error will like peter out to 1 as you get larger and larger. And this you can just do using like a gradient descent, for example, some kind of numerical optimization. Then you compute the new sigma. So now you're going to have a smaller median error typically. And so you compute a new sigma, and then you choose the parameters that minimize your robust error, and then you keep on repeating 2 and 3 until you converge. Question?
Is it similar to regularization in machine learning with like a sigmoid activation function?
So the question is whether this is similar to regularization, where you have like with a sigmoid activation function. Actually, I would say it's a bit different. So the main difference is that in regularization, you're saying that you have some prior on your parameters. For example, you don't want your like m and b to be too far from 0. Or like in the case of a classifier, you don't want any feature to have too much weight. And in this case, we don't really have a prior on our parameters, but we're just we're changing the loss function. So in classification, for example, you can do L2 logistic regression or L1 logistic regression. and it's a different model for how much you pay to get something wrong. All right, so let me show you a demo in MATLAB now. And I'll also show you how, so first I'll go through the code. And this is posted. All right, so I've got a bunch of methods here. You can input the number of points, the number of outliers, the noise, the method, and then I've just hard-coded here the slope and the y-intercept for the line that's generating these points. So when I call this, it's going to generate some points along the line, and then this is all plotting code. So when I generate the line, I generate my x's first, so I generate x's randomly along my axis, and then I generate the true value of y, and then I perturb that by some noise, and I move the points in both the x and the y direction in some, So I'm moving the points perpendicularly to the line. So the total least squares is my best model in this case, according to the noise that I've generated. If I move the points just vertically, then the regular least squares fit would be the best model. Okay, so least squares is pretty simple. So here I take as input the set, and I'll show you how these algorithms work under different conditions in a moment. But first, I just want to show you how the solutions are computed. So I'm given my points x and y, and I want to fit a line to them. Make sure that you guys are seeing the same thing as me. OK, good. So then I create my A coefficient matrix. And as I said before, it's just all the x's in the first column and a bunch of 1s in the second column. My b in the form of ax minus b squared is what I want to minimize, is just my column of y values. I do my pseudo inverse, which is a backslash b. And that gives me my parameters. So the parameters are m and b. Right? Total least squares, the second method that we talked about, is just a different coefficient matrix. So again, it's the x column minus the mean of x, and the y column minus the mean of y. I do the eigenvectors and values of A transpose A, and the eigenvector I want is the one that corresponds to the smaller eigenvalue, which is the first one that I spits out. Then I get A and B from this P that I solve for, and then remember that C is just minus 1 times A times the mean of x plus B times the mean of y. And my error is here. So then I'm just converting from the homogeneous form to slope-intercept form so that I can compare to the true values, because I specified my values in slope-intercept form. Then the final method is robust least squares. It's slightly more complicated, but still not crazy. So I do a least squares fit. I get my initial m and b. I look at my error. And here I'm just doing the regular least squares instead of total least squares, although I could have done either. Get my median error. Then my sigma is equal to my median error. Then I'm just going to do 7 iterations, because it's just demo code, and get my error, or minimize my error using this MATLAB numerical optimization method, fmin unconstrained, and compute my error, get the new median of the error, and then update my sigmas. This is not generally a good thing to do. It means that I'm dynamically expanding my array, which means that MATLAB is going to copy a new array and then fill it in. But it's fine right now. So then m and b, I get my m and b from this, and then I'm plotting it. OK, so let's show how they work. So let's pull this over here. And I want to, oops, it's doing the same thing over and over. OK, so I want to do, let's say, endpoints. Oops. Endpoints. Let me just move my laptop over, because it's kind of hard to see what I'm doing. Equals 10. outliers equals 0 initially, noise equals 0.01, methods equals, let's do LSQ and total least squares, and demo line fit. Demo line fit endpoints. Oops. Let me know if I mistype something. Endpoints, outliers, noise, methods. Okay, so let me pull that figure over. And so here's just, this should work well. I just generated 10 points according to a small amount of noise. Now we can see what happens as we increase the noise. Also, I'm going to change the slope here to -2. Okay, so let's do let's do 50 points, and we'll do 5 times the noise. Okay, so they're both doing pretty well. Can do it a few times. So here you can see the predicted value of M and the true value. Oh, I think I didn't change I forgot to save that. And I also had a typo. -2. Sloop. Okay. So the ground truth is -2.1. Least squares is predicting -1.88.94. And total least squares has a better prediction, more accurate prediction of -1.96.98. That's because it's a better fit to the noise model. So if I generate that some more times. Now if I increase the amount of the noise, let's say that I just increase it, but I keep the number of points small, then you should expect with least squares that I'm going to have a lot of variance in my estimate because due to the noise. So there it got it pretty right, but with different samples I can get more or less error. They're still both pretty good. Even with 10 points and a moderate amount of noise, they're able to get a reasonable fit. Now if I increase the noise to something that's really large. So now you can see with a large amount of noise and a small amount of points, then least squares can have more trouble. And especially in the case of regular least squares where the error model doesn't really fit the noise, it tends to be more off in the slope. But if I get unlucky with my noise, then I might have a bad fit. Now as I increase the number of points, I should expect that eventually I'm going to still have a reliable estimate for my fits, especially in the case where I correctly modeled the noise. So now with 100 points and still a lot of noise, total least squares is pretty much right on target, while least squares is way off because it's not modeling the noise correctly. Right? And if I go to, as I increase, for any amount of noise, if I increase the number of points enough, then I'll still have a good fit, as long as my error model is a good fit to the noise, or it accounts for the noise in an appropriate way. So this kind of looks like a mess to us, but total least squares is able to get a very accurate estimate out of it. The more points you have, the less sensitive you are to noise. But the same is not true for outliers. So if I say, so now let's say I just go back to 10 points to start. And I'm just going to have one outlier out of the 10 points. And let's say my noise is a bit more manageable, so 0.01. So in this case, the outlier was not too far off, so everything's OK. So as the outlier, here the outlier is still not too crazy, but it's pulling, that one outlier out of 10 is pulling both the points significantly towards it. Right? So if you get a really unlucky with the outlier, it can deviate the entire line away from those points. Now, if I increase the number of points and I increase the number of outliers, so let's say I've got 100 points and 10 outliers, then these methods are still going to have significant problems. Actually, they're sort of doing okay. Because the outliers, so here it got less lucky with the outliers. Most of them fell on one side. But these methods, depending on your outliers, it's also helping that I'm plotting a line near the center and generating outliers randomly around the center. But if I have, say, can beef up the outliers. All right. So as I increase the number of points and increase the number of outliers, I'm still going to maintain errors, no matter how high the number of points and outliers gets. So now I can add in robust least squares. RLSQ, I think it was. So this plot that I'm about to drag over shows you the median error as I go through the iterations of robust least squares. So in the first iteration from least squares, the error was 0.25. And then it quickly drops down to like 0.03. And then it pretty much stays there. So you can see over here, too, that my least squares is way off. My total least squares is also pretty far off. And my robust least squares is nearly perfect, because the robust least squares can basically, it discounts these points. Once they have a large enough error, then they don't contribute to the loss function. They just are a constant loss. Right? So I'll just run that a few more times. So robust least squares, again, nearly perfect. The other ones are significantly off. Right? So every single run, robust least squares is really close to the correct answer. And least squares and total least squares are pretty far off in the slope and the y-intercept. Right, so that's one solution. So I should also mention that there's other ways to search for parameters when you don't have a closed form solution. So in these line fitting methods, we have a closed form solution, just the pseudo inverse, or solve for the eigenvector with the smallest eigenvalue. In other problems where you have a nonlinear optimization, you might not have a closed form. So for example, in robust least squares, I was able to just sidestep that by calling the MATLAB function. But the MATLAB function has to do some search over parameters in some way in order to try to minimize that nonlinear expression. One way of doing that is a line search. That's a really easy optimization method. So if you just have one parameter, it just means that you step over all the values of that parameter. Or if you want, you could do like a bisection where you check the middle and then you check a couple of parameters and then you kind of try to zero in on the sampling values that are closest to your currently best parameter. It depends how noisy, how crazy your error function is. So even if your error function is like going all over the place, you can minimize it just by searching all the values across the line. But if you have, the generalization of that is a grid search. So there on one axis you have like your A parameter. On the other axis you have your B parameter. And then you want to try all possible values of A and B along with some step size. And then choose the values that minimize your error function. So obviously, this breaks down if you have 7 or 8 parameters, because then you're doing like a 7 or 8 dimensional search. The number, if you were just trying 10 parameters for each one, 10 different values for each parameter, then that would be 10 to the 7th or 10 to the 8th parameters you'd have to try. And if your error function is expensive to evaluate, then you're not going to be able to do the computation. So a line search is good if you have one parameter. A grid search might work if you have a couple of parameters. But these don't work well if you have a lot of parameters. The other thing to note is that it's actually, rather than a grid search searching for points on a grid, it's actually better to randomly sample points on your grid and try those parameters. Because if there's correlations in if one parameter is a lot more important than another parameter, then that gives you a better sampling of each parameter separately. That's kind of a side note, but something to keep in mind. The other solution is gradient descent. So there you provide some initial position. You have some initial guess at your parameters. You estimate the derivative of your error function at your current set of parameters. And then you move in the direction to decrease your error function according to that derivative. So that's a local search for parameters by following the gradient. This will give you a locally optimal solution, meaning that if you imagine your error function on this hill, and I start here, I'm going to go down to the lowest point until moving in either direction increases my error, and then I'm going to stop, even if there was a better solution somewhere else. So you can manually sample many different positions and then do gradient descent. But in general, you're not likely to have a guarantee that you found the best solution. So there's another class of problems, or class of methods that I want to go into more detail on. These are used quite extensively in computer vision, which I kind of call hypothesize and test methods. So the idea is that first you propose a set of parameters. There's some variance. You could try all possible parameters. You could say that a point is going to vote for all the parameters that agree with that point. That's a Hoff transform. You could just repeatedly sample a small subset of points and then solve for parameters with those points, like ransack, which those two algorithms I'll describe soon. Then, given your parameters, you compute the score of your error function or goodness of fit function. So if you expect that there's outliers, then a good score is often how many points agree with this current model. So how many points are within some epsilon error. And then you choose from all the different sets of parameters you've tried, you choose the one that gives you the best score. And then possibly, after choosing the inliers, which are the points that agree with your model, then you might do a least squares fit to refine the parameters. So the first method that I'll describe is the Hoff transform. So this is kind of interesting because it kind of inverts the problem. So instead of asking what is the model that agree, or what is the model that agrees with all of my sets of points, you take each point and you say, what are all the models that agree with this point? And then what are all the models that agree with this point? And then what are all the models that agree with this point? And then which models are in common among many of these points? So you create a grid of parameter values. Each point votes for a set of parameters, and I'll illustrate this in a moment, incrementing those values in a grid. Then you find the maximum or local maximum in the grid. So for example, in the y equals mx plus b formulation, we, given a point of yx, there's a whole space of lines that would satisfy that point. It's basically all the lines that pass through that point at xy is a set of possible parameters according to that one point. Then if I get a new point, there's another set of lines that could pass through that new point. But note that these two, the set of possible parameters that pass through this point and the set that pass through this point, intersect at just one point, which corresponds to the line that passes through both of them. And then as I get more points, then I can again keep on accumulating the sets of parameters that agree with each point, and then find the parameters that the most points agree with. So in practice, you have to accumulate votes. So you grid the m and the b values, which means that you block them into discrete values. And then every time you see a point, you count how many cells the possible parameters for that point, or you count which cells the parameters for that point fall through. So for like this point, you count and say that I'm going to add 1 to this bin, and 1 to this bin, and 1 to this bin, and 1 to this bin, because each of those bins agrees with the set of parameters that fits those points, that point. And if you have, so if you have a little bit of noise in your points, then you might have, there might be a couple of values that have a large accumulation of points. So you'll choose the local maximum. So in this case, it would be 11. So in this case, well, in the illustration, it's saying that there's 11 points that agree with this estimate of your slope and intercept. So one problem with a problem with this form of the linear Hough transform is just that you can't really deal with vertical lines again, because again, the y equals mx plus b form isn't great for that, because then the slope goes to infinity and you can't really grid up to infinity. So in practice, if people are using Hough transform for line fitting, which is one of the original applications, you use a different representation for the parameters of the line. So here we use this polar representation, which is basically thinking of the line as having some distance to the origin and some slope. And then you represent a point on the line as x cosine plus y sine theta, x cos theta plus y sine theta, where theta is like the slope, and equals rho, where rho is the distance of the line to the origin. And then now in this parameter space, every point gives you a sinusoid. And so the concept is the same, that you keep on accumulating these sinusoids in the parameter space that correspond to the points in the xy space, and then you find the value of your rho and theta where most of the sinusoids that covers most of the sinusoids. So here, this is just showing the y theta form rho theta form of a line. So this is an example. If these are my features on the left side, then I'm doing this accumulator in the Hough space. And so this point is where I've got like a maximum of my votes. And so this will be the set of parameters. This parameter here is the one that best accounts for the set of features. Right? Where here the x and y axis are rho and theta. Now, one downside is that if you have some noisy data and you bin your parameters too finely, then you might end up with many local maxima, because you could fit many points if you're trying to fit lines very closely to these points, you could fit many such lines. For example, one through these points and a different one through these points. And those will show up as different local maxima. So you would typically adjust your grid size or smooth. So if you make a bigger grid, for example, then all the points will fall inside the same grid cell. In practice, I think it's a better solution to smooth than to make a bigger grid. But it depends on like how many parameters you have, for example. So the Hough transform is can be good at dealing with outliers. The reason that it's good at dealing with outliers is that if I have a random point that's off on its own over here, then it's just going to have a sinusoid that's like unrelated to most of these, and it won't really affect the maximum. And if you have lots of these random points, they're not going to agree with each other, so it's not going to agree with the parameters that have the most votes. But it's not very good at dealing with a lot of noise. So it makes sense in applications where you have outliers but not super high noise. So here's an example on a real-world image. I've got this Monaco image with my canny edges. And for each edge is voting in the rho theta space. And I can also use the orientation of the edge. In this case, I'm not doing that. I'm just treating each edge point as a generic point. But I could refine my Hough voting by saying that not only do I know that for example, this is on a line, but I know the orientation of that line because I know the orientation of the gradient. So I could vote in a smaller part of the parameter space and just vote for lines that are kind of roughly in this direction. So here's the accumulation of the Huff votes. Right now it kind of looks like a big tangle of spaghetti or something. But if I then find the peaks, so I find the local maxima, then this is the set of lines that it gives me. So it finds many of the true lines. These are all different local maxima. So I've got like the edges here. I've got some of these vertical edges. It also, though, often will find some, like inexplicably, some lines that don't seem to match up to any of the true gradients. So the way that I created this was I first found the bins that are local maxima, and then I looked to see which points voted for those bins. And so that's how I'm plotting like these segments. And the reason that you get lines like this is that I wasn't using the orientation of the edges. So it's true that you can pass a line like through this diagonally and hit many points. And so it's not like accounting for contiguity. Here's another example where each of these peaks will correspond to one of the bars on the parrot's cage. So just to do one more conceptual example. So let's say that instead of fitting lines, I want to fit circles using the Huff transform. Oh, there's my pen. All right, so I want to fit circles using the Huff transform. Then the equation for a circle is x minus x naught squared plus y minus y naught squared equals r squared. So let's say that I'm given a set of points x, y, and I'm trying to solve for the center of the circle. And let's also just for now say that my radius is fixed. So the first question to ask is, if I'm given a point, so let's say I'm given this point that I know is on the edge of the circle, then what are all the circles that pass through that point? So where are the centers of radius r of all the circles that pass through that point? Right, so yes, the answer was on a circle of radius r away from this point. So if I have, for example, like this circle, say this is r, will pass through that point, as will this one. My circles are not very circular. Right? And if I join up all these centers, so if I do enough of these and join up all the centers, then the centers of these circles will be a circle of radius r away from the observed point, xy. And you can see that from this equation, because if I just flip x naught and x and y naught and y, I'll get the same value. So then what I do is I basically, in my parameter space, I'm trying to solve for x naught and y naught. And every point that I see will be casting votes for a circle in this parameter space. And this will be like gridded up, and I'm accumulating votes within the grid. And so I'll have some point that's voting for these parameters, and then some other point that's voting for these parameters, and some third point that's voting for these parameters, and so on. And then eventually, I'll hopefully accumulate I'll accumulate a lot of votes for one of the cells, and then that tells me my center of my new circle. Now, if I wanted to solve for radius, then I would just have a three-dimensional histogram that I'm accumulating. So for every radius, I would cast votes for circles within that radius and step over all the different radii. Right, so in gridding, I would have a 2D cell array for every x naught, y naught, and every every radius. This is supposed to indicate like a cube of cells. So one thing to note is that this really is this can be effective if you've got a lot of outliers. Well, I guess I've got this slide here. So if you've got outliers, it's robust to them because all the points are voting separately, and you're basically finding the parameters that the most points vote for. It's also can be very efficient. It's faster than trying all sets of parameters, for example. The time depends on how many points you have to fit. And you can generate multiple good fits. So if you're trying to fit multiple circles or multiple lines to a scene, for example, or we'll use this in object recognition, if you're trying to fit parameters for multiple objects, then this allows you to do that. You're not just finding the single best answer. The bad things is that it can be sensitive to noise because perturbations in the input will like shift your votes in parameter space. And then there's some parameters that you have to figure out, like the bin size or smoothing parameters. And sometimes it can take some trial and error to find the best parameters. And then also it's not suitable for more than a couple of parameters because if you have 4 or 5 parameters, then your grid the number of cells in your grid grows exponentially. So it gets very expensive. So the Hough transform is used for line fitting. Also circles and ellipses. It's used for object instance recognition, which we'll talk about in the next class. And it's also used for object category recognition in some cases, where the parameters of the objects are the position in the image and the scale. So I'll give you I'll just give you a quick 2-minute demo of that, and then I'll talk about RANSAC in the next lecture. So just hang with me for a moment. So if I change, if instead of, I'll leave robust least squares and also do Hough. I'm guessing that's the name. Okay, good. So now this is the, so here, these are my points. Remember that I've got a lot of outliers, but a little bit of noise. And these are my votes in the Hough space. And I've got like this strong accumulation in the center. Here's rho, here's theta. And the Hough transform worked really well for estimating the line as well. And then the code is posted, so you can look at that. The Hough fit's a little more complicated, so I won't try to walk through it in a minute. But you can see how I accumulated the votes and found the local maxima and then converted that to the slope-intercept form. So next class, I'm going to talk about RANSAC, which is a great algorithm for fitting when you have a lot of outliers and a moderate number of parameters. And then I'll also talk about alignment, which is kind of the twin brother of fitting, where you're trying to find transformations that match 2 sets of points. And I'll show an application to object instance recognition. Thanks. I'll see you Thursday.